All right, so let's start with our project. We're continuing to try to make progress on it. And again, the purpose of this is to emphasize the real life importance of calculus modeling. We've modeled the wetlands here with a rectangle. Today, we're going to model it with a trapezoid. And on Wednesday, what I'd really like to do is I'd like to talk about how to think about this in a really, really powerful way, where you allow these costs to be parameters that you can change, like with a family of functions like section 4.4 that you've done some problems on. And we'll talk about more today. So that'll give us some power to really solve infinitely many problems at once. And that's kind of the amazing thing about it, is you can really solve infinitely many problems at once. That's pretty powerful. All right, so again, we've got over the regular terrain, to remind you, we've got two costs, the pipe itself and the installation cost. Those add up to $2.70 per foot. And then over the wetlands, we have an additional cost of $60 per hour, which converts to, excuse me, $2 per foot when you use the fact that you can dig 300 feet of trench in 10 hours. And that allows you to then multiply these numbers by numbers of feet, both over dry land and over wetlands, to get your total cost as a function of X, where for the rectangle, X was how far up along the side of the rectangle that you went. And now for this trapezoid shape that we're going to try, it's going to be something similar. So here again is our wetlands. And right before class, I drew a trapezoid that approximated that shape. And let's again mark some of the dimensions on here. This was again 3.5 centimeters, which according to the scale, 1 centimeter being 100 feet, this corresponds to 350 feet. Maybe instead of equals, I should put the arrows there. This one was again 1.7 centimeters. 1.7 centimeters. That corresponds to 170 feet. We need some new dimensions now. So the idea here, again, is to try to minimize cost. I hope it's intuitive. If I model the wetlands as a trapezoid like this, that probably the path that might minimize the cost would go through the wetlands perhaps about like this. Once it gets over there to this spot right here, it would be on dry land. So I'll just draw a line, a red line here along this side of the trapezoid and pretend that's on dry land. So this is the only part that's going to be on the wetlands. And then come down to B. Since it costs more to go through the wetlands, we kind of want to keep the length of the path through the wetlands as small as possible. On the other hand, if we made the distance through the wetlands longer and went something like this, we would make the total length of the path shorter. So it's not absolutely clear that we should minimize the path through the wetlands to minimize the cost. I mean, if we wanted to minimize the path through the wetlands, we'd probably go up like this, but that would make a longer path along the dry land. So it's not necessarily clear that it would minimize the cost because the path along the dry land would be longer. So what should we do here now? We should make some more measurements. Again, 1 centimeter is 100 feet. I'll start my measurement here. Sorry, can't really get this in here very well. Start my measurement at B here with the 10. And if I go up to this corner of the trapezoid, looks to be pretty close to 4.5 centimeters. Looking at the 14.5 there. I'll just go ahead and assume that's 4.5 centimeters on the map, which would then correspond to 450 feet in real life. The question now is, how long should this path be before I go through the wetlands? This is now an unknown, call it X. X feet. That's your unknown. Should I go just a little ways up here before cutting through the wetlands? Should I go like I drew it up here before going through the wetlands? Or should I maybe even go all the way up here before going through the wetlands? X is the unknown variable that your cost function is going to depend on. You want to write the total cost as a function of x. So that's our goal here today, is to write that as a function of x. This length here also depends on x. If x is small, if I only go along this side a short ways, then that length right there would be more like this and would be pretty long. This one's fairly short. If I made x go up a little bit higher, like to right about there, then that distance would be as short as possible. What should I call it? Maybe, I don't know, d of x for a distance that depends on x. That might be something I could call it, d of x. A distance that depends on x, d for distance. How in the world am I going to figure out what d of x is? I need a formula for d of x, and this would be the thing that I would multiply by the 4.7, right? Because that's the cost in dollars per foot of going through the wetlands. And the sum of these two, x and 450, would get multiplied by 2.7, which is the cost per foot of going on the dry land. How in the world am I going to figure out d of x? The key is to draw a triangle in here. Anytime you can draw a triangle in math, it's usually a good thing. About like that. Of course, triangles are nicest when they're right triangles. Unfortunately, this is not a right triangle in general. If x were maybe up about here, then it would be a right triangle. This could be a right angle, but it's not in general. So I can't assume it's a right triangle. With right triangles, you have the Pythagorean theorem that can be used. And you also have trigonometry, thinking about SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But we don't have that here. We don't have a right triangle. So what do? We maybe try to look things up. You know, you could Google working with a non-right triangle or something like that. Solving for a side in a non-right triangle. If you do that, hopefully at some point you would run across the law of cosines as something that applies to triangles that are not right triangles. And if you look at the equation here, c squared equals a squared plus b squared minus 2ab cos, what's that thing? That's a gamma, lowercase gamma. It kind of looks like the Pythagorean theorem to some degree, doesn't it? C squared equals a squared plus b squared. But then you have to subtract this thing. Well, the reason you have to subtract this thing is because it's not a right triangle. So gamma is this angle right there. C is this side. It's not a hypotenuse because gamma is not a right angle. Though if gamma were a right angle, then it would be the hypotenuse. And in fact, if gamma were a right angle, 90 degrees, cosine of 90 degrees is 0. This would simplify to the Pythagorean theorem. Does that make sense? If gamma were 90 degrees, if this were a right triangle, this would simplify to being the Pythagorean theorem. But in general, you have to allow for this term, and we do have to do that in our problem. So the square of the length of the side opposite the angle you're interested in is the sum of the squares of the other two sides minus 2 times the product of the lengths of those sides times the cosine on the angle. So it's kind of complicated, but let's see what it gives us here. So in this picture, what angle could I measure that would be constant no matter what x is? It's got to be this angle right there. That's the only angle that's going to stay constant even for different values of x, because if I change x, this angle definitely changes and this angle definitely changes. That's the angle that's constant. That's the angle that I can try to measure with my protractor here. Roughly speaking here. So I'm putting the origin of the protractor right there at the corner, putting this side, this line along the red line here. Having a hard time getting it exactly right. Okay, say right about there. Now look at where this angle is and follow it up here. It looks to be pretty close to 14 degrees or so. Maybe a hair less than 14 degrees. close enough that I'm just going to call it 14 degrees. Looking right there. Yeah, I'm just going to go ahead and call it 14 degrees. Okay. So according to the law of cosines, what would I like? I'd like to find a formula for d of x. The d of x is really like my c in this equation because it is the side length opposite the angle that I know. This is the side that is opposite from the angle that I know. So d of x squared, or if you prefer, go ahead and take the square root right away. D of x is the square root, right? You could solve this for c by taking the square root of both sides. Is a squared plus b squared, that's this side squared, x squared, plus this side squared, I guess I have to measure that. I got to measure the angle and also measure this length. This length will stay constant. Measured in centimeters here. It's pretty close to 5 centimeters. Let's just go ahead and assume it is. Five centimeters on the map, which corresponds to 50 feet, 500 feet in real life. Yeah. So that is the other side. I've got to square that. And then if you remember from the law of cosines here, let's go ahead and take a look at it again. 2 minus 2 times a times b times cosine of the angle. 2 times x times 500 would be 1000x, because 2 times 500 is 1000, times the cosine of the angle, cosine of 14 degrees. What is that going to be approximately? Square root of x squared. I'll just leave the 500 as 500 squared. Minus, I've got to use my calculator. Here's one time in this class where we're using degrees. So make sure you don't forget that. Cosine of 14 degrees should be close to 1 because cosine of 0 degrees is 1. Yeah, pretty close to 1 times 1000. Got about 970.296, say, times x. All right, that's d of x. And so now our cost function to minimize is going to be, call it c of x, 4.7 times d of x, 4.7 d of x, where d of x is this entire thing. To save time, I won't rewrite it. Plus 2.7 times the sum of x and 450. That make sense? Oh, we're so close. Let's go ahead and use Mathematica to minimize this. We might as well here. I'll go ahead and type in the d of x as a square root. I can do SQRT with a capital S. X squared plus 500 squared minus 970.296x. And then the c of x is 4.7 times d of x plus 2.7 times x plus 450. So we could get a rough estimate as to the answer by plotting this. Thinking about the picture, X is probably going to be somewhere in the ballpark of 2 or 3 or 4 or 500 feet. So if I went from 0 to 600, that might be enough. Yep, that looks like it's probably good. Looks like our minimum cost, well, the value of X that's going to minimize it is going to be close to 400 with a minimum cost close to 3,000. Is that really what it is exactly? We'd have to set the derivative equal to 0 and solve for X. Just a little bit bigger than 400. And C of 400.254 is a little less than 3,000. So we've pretty much quickly solved the problem, right? There's the answer. We should, assuming this is a trapezoid shape, we should lay pipe along the dry land here, the X direction, until X is up to 400.254 feet. Close enough to 400 feet to maybe even just go ahead and just do 400 feet. And then our minimum cost itself will be about $2,990. Okay, so there's a practical problem and a practical solution. Now, the swampland's not exactly a rectangle. You know, you'd probably want to come back here and say, okay, what does this really mean? It's not exactly a rectangle. You'd want to maybe you're just trying to approximate it. And again, X was what, close to 400, I forgot it already, 400 feet? Close to 400 feet. So that's 4 centimeters. So somewhere in the ballpark of, there's a 14, there's a 10, somewhere in the ballpark of right around here is where you're going to cut through the wetlands. So pretty close to being almost parallel to A there in the east-west direction, or the same north-south spot, approximately, which makes intuitive sense, I guess. Again, what we'll do on Wednesday is we'll generalize this. And again, this is going to be the more powerful thing. Coming back to thinking about the costs, we'll ask what happens when we allow these numbers to change, and how does it affect the answer? That's the more important thing. How sensitive is the answer to changes in these costs? Is it more sensitive to changes in this cost or these, or what? That would be an interesting thing to know and probably a useful thing to know.